Forget the gentle arcs of land-based aviation. On a carrier, an aircraft is born in violence and returns in a controlled crash. 3 seconds of electromagnetic fury hurl 30 tons of metal and fuel into the sky. 100 meters of steel cable snatch it back from the edge of oblivion. In this world, the difference between a combat-ready asset and a fireball on the deck is measured in microns of turbine blade tolerance and milliseconds of software response. This is the brutal reality that shaped the Shenyang J-15, China's first attempt to master the carrier jet. Plagued by underpowered engines and treacherous flight controls, the original Flying Shark was a testament to the immense difficulty of the task. Its evolution into the catapult-launched J-15T is therefore more than an upgrade. It is the story of a nation wrestling with the fundamental physics of naval power and finally beginning to win. To ensure you don't miss future in-depth analyses like this one, be sure to subscribe. The genesis of the aircraft, known to NATO as the Flanker X-2, and more poetically by its creators as the Fascia, or Flying Shark, is a tale of strategic necessity, industrial opportunism, and a rather flexible interpretation of international intellectual property norms. In the early 2000s, the People's Liberation Army Navy, PLAN, faced a classic chicken-and-egg problem. It had acquired the unfinished hull of the Soviet aircraft carrier Varyag, which would eventually be reborn as the Lining, but it possessed no aircraft capable of operating from its deck. The logical choice was the Soviet-designed Sukhoi Su-33, the navalized variant of the formidable Su-27 flanker, specifically designed for this class of carrier. However, negotiations with Russia for a purchase collapsed. Moscow, wary of China's burgeoning reverse engineering capabilities demonstrated by the Shenyang J-11B, a modified copy of the Su-27SK, reportedly demanded a large minimum order to justify restarting the dormant Su-33 production line, a price Beijing was unwilling to pay. The solution, as it often does in such geopolitical impasses, emerged from the post-Soviet industrial diaspora. In 2001, China acquired the T-10K3, an unfinished Su-33 prototype, from a test facility in Ukraine. This single, non-flying airframe became the Rosetta Stone for China's carrier aviation ambitions. The J-15 program was officially initiated in 2006, with the Shenyang Aircraft Corporation tasked with dissecting the Ukrainian prototype and creating a domestic equivalent. It is crucial to understand that the resulting J-15 was never a simple one-for-one clone. While its airframe is structurally based on the Su-33, inheriting its distinctive three-surface configuration with canard foreplanes, folding wings and stabilators, and a strengthened undercarriage, its internal systems were a hybrid of reverse-engineered Soviet design and indigenous Chinese technology. Rather than replicate the Su-33's dated 1980s-era avionics, Shenyang integrated the more modern digital systems developed for its land-based J-11B fighter. This decision made the J-15 a multi-role platform from its inception, a significant departure from the Su-33's primary focus on air superiority. This act of industrial archaeology saved China years, perhaps a decade, of fundamental aerodynamic research. However, this shortcut came with a hidden and substantial engineering debt. By copying a mature airframe without access to the full suite of design data, wind tunnel results, and stress testing information, Chinese engineers were left to fill in critical blanks on their own. This was particularly true for the complex interplay between the airframe's unique aerodynamics and the flight control system, a challenge that would later manifest in a series of tragic and costly failures. The rapid success in replicating the physical form of a carrier fighter masked a far more difficult and protracted struggle to master its soul. The initial operational phase of the J-15 aboard the short takeoff but arrested recovery Stobar carriers Liaoning and Shandong can be best described as a period of tethered ambition. The aircraft, while visually impressive, was fundamentally hobbled by the physics of its launch method and the immaturity of its core systems. The upward curving ski jump ramp, a simpler and cheaper alternative to a catapult, imposes severe penalties on an aircraft's maximum takeoff weight. While the J-15 theoretically possessed a respectable payload capacity of up to 6,500 caloric, approximately 14,000 pounds, the reality of a ski jump launch from the carrier's 105-meter or a 195-meter positions slashed this to a near-anemic practical limit, in some cases as low as 1.5 tons. This created an inescapable operational dilemma. A J-15 could launch with a meaningful fuel load for a combat air patrol, or it could carry a meaningful load of anti-ship or long-range air-to-air missiles, but it could not do both simultaneously. This single constraint relegated the Flying Shark to a primarily defensive role, blunting its teeth and drastically curtailing the carrier group's power projection capabilities. Compounding this aerodynamic handicap were severe and persistent reliability issues. The program was plagued by problems with both its Russian-supplied Saturn AL-31F engines and, more critically, its early-generation indigenous Shenyang WS-10 turbofans. The AL-31F, while a known quantity, suffered from a limited service life and was prone to nozzle malfunctions, while the early WS-10 variants were notoriously unreliable and lacked the requisite thrust to get the heavy airframe off the deck with a full load. The harsh maritime environment, with its high salinity and humidity, only exacerbated these engine woes. Even more alarming were recurring problems with the aircraft's flight control system, FCS. Reports from multiple crashes pointed to an unstable FCS as a key contributing factor, suggesting that the software and hardware adapted from the land-based J-11B were not fully compatible with the different aerodynamic characteristics and demanding landing profile of the canard-equipped, carrier-borne J-15. This dangerous combination of underpowered engines and a temperamental FCS led to at least 4 known crashes, several fatalities, and at one point, the grounding of the entire J-15 fleet. The aircraft's operational availability was reported to be a dismal 42.8%, meaning that at any given time, less than half the fleet was fit to fly. In this light, the early J-15 was less a weapon system and more a brutal, high-cost training apparatus. Its primary value was not in its combat potential, but in its role as the sole platform through which the plan could begin the long, arduous process of building institutional knowledge. Every launch and recovery, however light the payload, was an invaluable lesson for pilots, deck crews, and commanders who were starting from a knowledge base of zero. The failures of the Stobar J-15 were, in essence, a necessary and painful tuition payment for admission into the exclusive club of carrier-operating navies. The recognition that ski jump carriers represented a strategic dead end for a navy with blue water ambitions drove the parallel development of China's first catapult-assisted takeoff barrier, arrested recovery, catabar carrier, the Type 003 Fujian, and a new generation of the Flying Shark capable of operating from it. This metamorphosis resulted in the Shenyang J-15T. For years, this upgraded variant was referred to in media reports as the J-15B, but the officially unveiled production model now carries the J-15T designation, a name that covers both the initial prototypes and the series production aircraft, rendering the J-15B moniker effectively obsolete. The transformation from the original J-15 to the J-15T is far more profound than a simple letter change. It represents the unlocking of the airframe's full potential. The most critical modifications are centered on the nose landing gear, which has been completely redesigned and massively reinforced to withstand the violent stresses of a catapult launch. It features a longer and wider shock-absorbing oleo strut and an integrated catapult launch bar, the crucial mechanical link that hooks into the shuttle of the carrier's launch system. The internal airframe structure was also significantly strengthened to distribute these immense forces without compromising structural integrity. This new variant was designed explicitly for the Fujian's Advanced Electromagnetic Aircraft Launch System, EMALS, a technological leap that bypasses steam catapults entirely. The successful completion of catapult launches and arrested recoveries of the J-15T from the Fujian in 2025, alongside the new J-35 stealth fighter and KJ-600 airborne early warning aircraft, served as the definitive validation of China's entire modern carrier ecosystem. This was not just a test of a plane or a ship. It was the successful culmination of a decade-long codependent engineering effort, demonstrating a maturation from reverse engineering individual components to designing and integrating complex systems of systems. Critically, the J-15T retains the ability to operate from the older Stobar carriers, providing the plan with significant operational flexibility and a way to upgrade the combat power of the Liaoning and Shandong air wings. A detailed examination of the J-15T reveals a platform that has evolved from its 1980s Soviet roots into a thoroughly modern 4.5 generation fighter. The airframe, with an empty weight of approximately 17,500 kilos and a maximum takeoff weight of 33,000 kilos, makes extensive use of composite materials to a greater degree than its Su-33 progenitor, reducing weight and improving aerodynamic performance. The most significant leap forward lies in its propulsion. The J-15T is powered by mature variants of the indigenous Shenyang WS-10 afterburning turbofan, likely the navalized WS-10B or WS-10H. These engines deliver a substantial increase in power, providing between 135 kN and 144 kN of thrust with afterburner compared to the 122.6 kN of the Russian AL-31F. This boost gives the J-15T a thrust-to-weight ratio exceeding 1.0 in certain configurations, a key metric for fighter performance, and reflects a newfound confidence in the reliability of domestic engine technology, an absolute prerequisite for the high-stakes environment of carrier operations. The aircraft's sensor suite has undergone an equally dramatic modernization. The single most important upgrade is the replacement of the old mechanically scanned array radar with a modern active electronically scanned array AISA system. This is visually identifiable by the aircraft's new lighter gray radome, which has a distinctive canted connection to the nose and the conspicuous absence of the long pitot tube that characterized earlier flanker variants. This AISA radar is credited with a detection range exceeding 200 kilometers, enabling the J-15T to see farther and engage targets with greater precision and resistance to jamming. The aircraft also features an updated infrared search and track IRST system mounted forward of the cockpit, a passive sensor that is particularly useful for detecting low observable aircraft at shorter ranges. The cockpit itself has been transformed into a modern glass interface featuring a large, wide-angle holographic head-up display, HUD, and, in a nod to its new operational reality, grab bars for the pilot to brace against during catapult launches. This suite of upgrades demonstrates a pragmatic and efficient engineering philosophy, leveraging the proven aerodynamically superb flanker airframe while integrating mature, cutting-edge subsystems developed across China's broader aerospace industry, particularly from the J-11D and J-16 programs. The transition to catabar operations fundamentally redefines the J-15T's combat role, transforming it from a light-duty defensive interceptor into an authoritative strike and air superiority platform. Freed from the tyranny of the ski jump, The J-15T can now utilize its full payload capacity, estimated at up to 12 tons of fuel and ordnance. This is a revolutionary increase that allows the aircraft to fulfill its multi-role potential. It retains its internal 30mm GSH 30-1 cannon with a 150 rounds and can carry weapons on 12 external hardpoints. The modernized avionics and pylons enable the J-15T to wield China's most advanced air-launched munitions. For air-to-air combat, this includes the PL-10, a highly agile short-range missile with high off-bore sight capability, and more importantly, the PL-15 Beyond Visual Range air-to-air missile. The PL-15 is a genuine game-changer, boasting an estimated operational range of 200-300 kilometers, which significantly outranges the American AIM-120D AMRAAM. Equipped with an active radar seeker and a two-way data link for mid-course updates, the PL-15 allows the J-15T to engage hostile aircraft from standoff distances. For maritime and land attack missions, the aircraft can carry a variety of munitions, including the subsonic YJ-83K anti-ship missile and the supersonic YJ-91, which can function as both an anti-ship and an anti-radiation missile for suppressing enemy air defenses. The combination of the J-15T's long-range AESA radar and the extended reach of the PL-15 missile creates a formidable defensive shield for the planned carrier strike group. A J-15T on combat air patrol can detect and engage incoming threats well before those threats are within range to launch their own weapons, fundamentally altering the tactical geometry of a carrier versus carrier engagement and dramatically enhancing the survivability of the entire naval formation. While a direct side-by-side tabulation of specifications is often the clearest method for comparison, the narrative format requires a more integrated approach. The following analysis will therefore weave these comparative data points into a cohesive assessment of the J-15T against its progenitor and its primary rivals. Compared to its direct ancestor, the Sukhoi Su-33, the J-15T is in a completely different class. The Su-33 has been a victim of benign neglect, receiving only minor upgrades since its introduction and retaining a 1990s-era cockpit with mostly analog instruments and a mechanically scanned Enrozo-1 radar. The J-15T, with its AESA radar, glass cockpit, extensive use of composites, and compatibility with a new generation of munitions, is a far more capable and versatile multi-role aircraft. The more relevant comparison is with its contemporary Western counterparts, the Boeing FAA-18E F Super Hornet and the Dassault Rafale M. Against the Super Hornet, the J-15T represents a classic contest of kinematic potential versus system maturity. The J-15T is a larger, heavier aircraft with a maximum takeoff weight of 33,000 kilograms versus the Super Hornet's 129,900 kilos. It boasts superior flight performance in several key metrics, including a higher top speed, approximately Mach 2.4 versus Mach 1.8, and a greater service ceiling, around $20,000 versus $15,000. Its WS-10 engines produce more thrust than the Super Hornet's General Electric F414s, and its larger airframe allows for a physically larger AESA radar aperture, which in theory could provide a raw advantage in detection range. The Super Hornet's strengths lie in areas harder to quantify on a spec sheet. Its highly mature and combat-proven AN/APG-79 AESA radar, its superior sensor fusion and data networking capabilities, its advanced electronic warfare suite, and its more refined, low observable characteristics. The matchup with the Dassault Rafale M highlights a different contrast in design philosophy. The Rafale M is a medium-weight fighter, significantly lighter and more agile than the J-15T, with a maximum takeoff weight of 24,500 kilograms and a higher G limit, Pl 9G versus almost 8.5 G. While its top speed is lower at Mach 1.8, it possesses the ability to supercruise, fly supersonically without afterburner, and is renowned for its world-class Spectra integrated electronic warfare suite and the seamless sensor fusion between its RBE-2AA ISA radar and its frontal sector optronics, OSF IRST system. Ultimately, the J-15T embodies a brute force approach, leveraging a large, powerful airframe to maximize speed, altitude, and payload, exemplified by its pairing with the very long-range PL-15 missile. Its Western rivals, while still potent kinematically, place a greater emphasis on situational awareness, data fusion, electronic survivability, and lower observability. It is a contest between the longer spear and the more skillfully wielded sword, where the outcome would likely be decided not by the aircraft alone, but by the quality of the surrounding network of early warning aircraft, electronic warfare support, and command and control systems. The introduction of the J-15T, in conjunction with other new platforms, signals a profound shift in the strategic role and future prospects of China's carrier air wings. The early narrative of the J-15 as a mere interim fighter, destined for complete replacement by a fifth-generation aircraft, now appears overly simplistic. Instead, the J-15T is poised to become a permanent and crucial pillar of a sophisticated high-low capability mix, operating alongside the new J-35 stealth fighter. The future air wing of the Fujin and its successors is now clearly defined, comprising a synergistic combination of J-15T heavy multi-role fighters, J-35 stealth fighters, J-15D electronic warfare aircraft, and KJ-600 airborne early warning and control AEW&C platforms. In this architecture, the J-35 will serve as the door kicker, using its stealth to penetrate contested airspace, gather intelligence, and clear a path for the main strike force. The J-15T, with its massive payload capacity, will function as the missile truck and bomb truck, launching volleys of long-range standoff weapons like the PL-15 from a safer distance, cued by data from the forward-deployed J-35s and the overarching eye of the KJ-600. This is augmented by the J-15D, a two-seat electronic attack variant analogous to the U.S. Navy's EA-18G Growler, which will provide vital jamming support to suppress enemy air defenses and protect the entire strike package. This doctrinal structure, a mix of stealth strike, heavy conventional firepower, electronic attack, and airborne command and control, is not an invention. It is a direct reflection of the modern U.S. Navy carrier air wing composition, which pairs the F-35C, FA-18EF, EA-18G, and E-2D Hawkeye. This convergence of doctrine is arguably more significant than the technical specifications of any single aircraft. It demonstrates that the plan has moved beyond simply copying hardware and has now fully absorbed and is actively implementing the complex, network-centric operational concepts that define modern carrier warfare. The J-15T, therefore, is not a stopgap. It is the indispensable heavy lifter, the provider of affordable mass and long-range firepower that enables the more advanced and likely more expensive stealth assets to be employed to their greatest effect. Its journey from a flawed copy to a credible catapult-launched predator is complete, and in doing so, it has become a load-bearing component in China's emerging architecture of global naval power. The true test of the J-15T will not be found in brochures or parade line flybys, but in the grinding arithmetic of sustained operations, the dull calculus of sorties per day, maintenance man-hours per flight hour, and the attrition curve of engines and avionics under salt air and constant use. A carrier air wing is less an assembly of singular miracles than an industrial process writ at sea. Its combat value is determined as much by the supply chain that feeds it as by the latest radar or missile it carries. In practice, this means the J-15T's contribution will be measured by how reliably it can be cycled through the deck, launched, tasked, recovered, refueled, rearmed, and relaunched with the predictability of a clockwork machine. That predictability is the product of hundreds of small innovations as much as of headline changes. It is found in the redesigned access panels that let a maintenance crew reach a hot section fast and safely, in corrosion-resistant coatings and sacrificial anodes on vulnerable control surfaces, in the spare engine logistics that determine whether a carrier force can sustain a week of high-tempo sorties or will be stranded by a single turbine failure. The Chinese industrial response to this challenge has been incremental but relentless. Procedures written into checklists, specialized shore support ships assigned to engine swaps, modular avionics racks that can be swapped in a matter of hours instead of days. Those are the kinds of efficiencies that convert a potent aircraft into a useful one. They also expose the thin line between operational competence and systemic fragility. An enemy who understands that attrition and downtime, not a one-on-one duel, will decide a protracted maritime clash can design campaigns centered not on shooting down fighters, but on grinding down the logistics that sustain them. This is the vulnerability any large, complex air arm must accept and then attempt to mitigate. Operational doctrine around the J-15T has matured into something that emphasizes redundancy and layered responsibility. Where earlier carrier planners might have imagined a small number of multi-purpose sorties doing everything, the revised model favors dedicated tasking. Some aircraft commit to long-range radar picket and missile control, others to persistent escort, still others to strike packs that can be rapidly reconfigured to carry anti-ship or land attack payloads depending on the unfolding picture. This doctrinal multiplication is not mere extravagance. It is a pragmatic response to the realities of modern sensors and networks. A long-range missile is only as good as the sensor that tells it where the target will be minutes from now. The J-15T thus becomes part of a distributed targeting chain in which the KJ-600, land radars, and space-based assets feed a common operational picture. That chain is only as effective as its weakest link, and so the J-15T program has driven investments not just in airframes and engines, but in data links, secure comms, and electronic protection measures. The invisible plumbing that lets a missile guided by a carrier-based radar receive in-flight target updates from a drone loitering hundreds of kilometers away. The human side of this system has evolved too, into a culture that prizes specialization. Where the early years forced pilots to be jack of all trades, the emerging model encourages crews to master narrower, more repeatable mission sets, to reduce error rates and increase reliability under stress. A pilot who has practiced the long-range intercept profile and the electronic attack response 100 times is exponentially more useful than one who has been trained only to get the airplane to the carrier. This emphasis on repeatable muscle memory reduces the fog of war in the cockpit. It also means training pipelines must produce not just technically proficient pilots, but teams, sensor operators, weapons officers, and deck control specialists, drilled to operate in a tightly choreographed tempo. The choreography extends to the deck itself. The choreography of tractors and ordnance crews, of fuel trucks and catapult technicians, each movement timed so that the next launch is not delayed by a single missing bolt. Such sequencing is the hidden art of carrier operations, and here the J-15T's increased weight and complexity have forced a painful but ultimately productive redeployment of manpower and procedure. Seen from an adversary's perspective, the J-15T changes the geometry of risk. It does not so much reduce the vulnerability of the carrier as stretch the threat envelope outward. With fully loaded J-15Ts on patrol, an enemy must respect a no-go distance measured in hundreds of kilometers rather than tens. Long-range missiles and a powerful radar make the carrier task force into a node that can contest sea control at a significantly greater standoff. That extension has important political consequences. In a crisis, a carrier that can generate credible strike options at long range becomes a bargaining chip. Its presence alters the calculations of diplomatic opponents even when it is not used. The fleet's ability to feed the political center with options, to promise a measured but potent application of force that stops short of war, is at least as valuable as its capacity to shred an enemy fleet. The J-15T thus functions as both an instrument of war and an instrument of statecraft, a duality that naval planners prize because it allows coercion without immediate escalation. Yet the platform's scale and role also ensure it will remain a target for asymmetric counters. Electronic warfare, cyber attacks against data links, maritime denial weapons, and the proliferation of long-range anti-ship missiles are natural responses to the problem of a numerically superior but visible air wing. The Chinese response has been twofold: hardening and deception. Hardening includes improved emission control procedures, frequency-hopping data links, rapid over-the-air authentication for cooperative targeting, and the installation of more robust self-protection suites. Deception takes the form of distributed sensors and decoys, unmanned surface and subsurface platforms that present false signatures or dilute an enemy's targeting picture. In exercises, J-15T groups have been paired with swarms of smaller unmanned systems whose purpose is not to kill but to complicate an adversary's sensor fusion algorithms, creating enough ambiguity that no single missile salvo can be reliably directed to a decisive kill. The combination of massed manned fighters and a distributed unmanned curtain is a distinctly 21st century approach to naval air operations. It recognizes that survivability in modern conflict depends as much on information entropy as on physical armor. Industrial learning will continue to be decisive. The J-15T's evolution has already rippled through China's aerospace sector, forcing improvements in manufacturing tolerances, metallurgy, and systems integration. Those advances lower the bar for future programs. Improved engine reliability reduces spare part pressure for other platforms. Better composites techniques accelerate stealth-related projects, and more sophisticated avionics integration makes multi-platform networking easier. This spiraling effect accelerates doctrinal change because it allows planners to envision operations previously considered too costly or fragile. There is, however, a countervailing danger in success. Achieving a comfortable operational tempo with a particular mix of platforms can create institutional inertia. Once an air wing is organized around the J-15T as the reliable workhorse, it becomes politically and logistically costly to shift resources toward wholly different architectures, say, a future in which unmanned fighters dominate the kill chain. The tension between exploitation of an existing, proven capability and investment in disruptive futures is a universal problem in military modernization, one that will shape the J-15T's long-run role. Export and influence are additional dimensions that cannot be ignored. A credible, cost-effective carrier fighter has diplomatic value. Selling or sharing a variant of the J-15T to partner states would not only bring revenue, but also standardize tactics and logistics among allies. The technological transfer inherent in such deals, however, carries strategic risks and domestic political complications. For Beijing, the calculus is delicate. Exporting too quickly might reveal vulnerabilities, while withholding technology could limit China's ability to bind partners into its sphere of influence. If exports occur, they will likely be to states whose needs and political alignment make such transfers sensible, and the exported variants will probably be downgraded in sensors and data links, sufficient to bolster a friend, not to make them appear. Ultimately, the story of the J-15T is the story of a Navy and an industrial base learning to think in terms of systems rather than singular platforms. The jet itself embodies trade-offs: size for payload, toughness for stealth, numbers for finesse. But those trade-offs make sense inside a coherent operational model that values persistence and mass in the face of modern sensors and missiles. It is a model designed to impose choices on an adversary: either accept contested seas and the risk of saturation, or concede areas of strategic interest. Whether that model will be decisive in a future conflict depends on many variables beyond the plane: the quality of enemy ISR, the effectiveness of missile defense, the resilience of logistics, and the political will to tolerate attrition. What is no longer in doubt is that the J-15T has moved from being a precarious experiment to a foundational element of naval power. It will not win every duel, but it can change the terms of the fight. And in modern maritime strategy, changing the terms often matters more than any single tactical victory.